So continuing with these points that I was using to make the case that you gain a lot from using an approach like this, let me touch on this issue of complexity management, right? So what happens, we as I mentioned before, we start collaborating with people in many different domains, and what happens there is that the models get very, very large. And as we see, we have this approach of validation via visual simulation. And if you can't manage the complexity of the models, you cannot understand the models, you cannot understand the results of the simulation anyway. So the approach becomes kind of much less useful. Complexity management is something that exists in conceptual modeling in domain modeling for many years, but it's very hard to find satisfactory solutions for large conceptual models in language, again, like UML or YAR or OW or OWL, because imagine what the difficulty of deciding how to break down a model or how to abstract a model when all elements in the model stand in the same footing, right? So take, for example, this problem of finding out what are the most important classes of the model, because you want to take a model with 500 classes and generate a summary of that model with 20 classes, but which really captures the gist of the model. How do you do this in a UML class diagram? Because everything you have there is just class and relations, right? So everything is a class. So how do you know which classes are more important? What people do is to use, they have to rely on topological properties of the model, right? But this, like for example, PageRank, people use a version of PageRank to do that and look at the classes that receive more relations, for example. But this ends being quite crude heuristics for many models, because sometimes you have classes which are very important, which are at the top of things, like kinds, for example, as we saw, that provide the identity to everything else, and they are not super connected. The connections, the density of the connections will be on the much lower, much further down in the specialization structure, in the taxonomic structure, right? But you cannot do better in a language that is neutral. So again, what I'm going to talk about here is the advantage of breaking with this kind of ontological neutrality. And I'm going to go a little bit faster on this. Again, suppose we have a model like this, right? Another example of a OntoUML model. You have a person. Sorry? Was there a question? So here we have people, which can be men and women, that can play these roles in the scope of this relator. You have phases, a taxonomy of phases. You have car rentals connecting customers, which, as we saw, you have here an instance of that row mixing pattern. You have car rentals would connect customers and responsible employees, people responsible for that rental, customers, which can be people, organizations, and rental cars, which are cars that are functional, right, and not under maintenance, and so on. So this is a very simple model. It's not that big, but suppose I want to do 3 operations here. One is abstraction. So create a summary of this model that really captures in a much restricted form, a much more abstract form, what this model is about. The other one is viewpoint extraction. So I want to look at this model from different viewpoints, focusing on different things. And the other one is modularization. So we have a technique for modularization that relies on this notion of relators or relational context. So the idea is that if you take this model, if you take anyone's life, for example, take my life, you could break it down in several different contexts: the employment, the marriage, the fatherhood, the citizenship, and so on, right? The membership in a given club, and so on, right? So in different contexts, you could look at the different roles which are playing different contexts and separate this model in these different relational contexts. So what we do here is you take one of these relators, for example, the marriage, and you start from there, look at the roles which are played in that relational context, and you follow those roles until you find the identity of the things playing those roles. So here, for example, this would be a self-standing context, if you like. Same thing here, you take employment and you look at the roles and you navigate until you find the identity provider for those roles. Same thing here. And in this case, it's a bit more interesting because you have two roles, right? Responsible employee and rental car, but then you have a role mixing. So you have to navigate downwards to the roles and then navigate upwards until you find the identity of those roles that can be played in the context of a car rental. And this is what sorry, there is a mistake here. This should include the rental car as well, the context. So you can take that model and break it down in these 4 different contexts. So you have the car rental, and that's everything you need to understand what a car rental is about, according to that model. You have the employment, you have the car ownership, and you have the marriage. And these packages or these modules, these clusters, take the name of the corresponding relator. So this is a very simple technique. The only way you can do this is because you're relying on this ontological semantics. We have just published a paper now at SOCIM in which we show that this is very computationally interesting, right? So it has low computational complexity. So it's important because you want to do this with very large models. And more importantly, that the modules you generate are very intuitive to people. So we actually did an experiment there as well, comparing to different methods for modularization. And there is a very strong evidence that people would prefer the modules generated by this. Another operation is this one. So imagine I have this model here, right? That talks about people and deceased living people and customers and corporate and personal customers and suppliers and so on. And what I want to do is to generate this summary of this model. And this summary will say, you know, this domain, you have 2 things, people and organizations. People have contractual relations with organizations. Organizations can have contractual relations with organizations. Organizations can play these roles of supplier in both relations, sometimes as corporate customers, sometimes people as personal customers, and people can have a life status, an organization have an organizational status, right? This is very simple. We have basically 4 rules of transformation in which what you are trying to do is to basically take all mixins, project down the shared information and project up until you reach the level of kinds. Again, if we compare this with the alternative methods, instead of, one of the most used methods for model abstraction has more than 100 rules, and it's non-deterministic. It's completely dependent on the order in which you apply the rules. This is a deterministic method that is computationally very efficient. So it's tested with really large models with 10,000 classes. And it's defined by 4 simple rules. A third operation is this viewpoint extraction. So imagine if I look at this and I want to know what are the kinds of things that exist in this domain. Basically 3: people, organization, and cars. People are specialized in the 2 subkinds. So the actual things which exist here are men, women, and car agencies. People are specialized in these different phases. Cars are specialized in these different phases. The relations which exist in this domain are these 4 relations: marriages, employments, car ownerships, and car rentals. And these are established between this kind of entity. So a car ownership is a relation between a car agency and a car. A car rental is a relation between a customer, a responsible employee, and a rental car. And then we look, what are these roles? Who can play these roles? And then we can look at the roles which are played by entities of multiple kinds. So a car can play the role of a rental car or an organization of corporate customer, and a person, these roles of a husband and a wife and responsible employee and personal customer. And a customer is exactly the instantiate of that pattern we saw before. In fact, these viewpoints are aggregation of those patterns, right? You are taking the model and you are taking views which are aggregations of all those different patterns. Again, very efficient from a computational point of view, very precisely defined and with a deterministic result. So you could take that model and look at, these are all different perspectives, right, on the model. So you can break it, you can abstract, that's a different model. You can create these modules, which are self-standing portions of the domain, and you can break it down in these different viewpoints, which are which concentrate in different portions of those patterns. Once we have this model, we can transform this model to many different types of languages, right? So, I mean, this is, I'm sure this is obvious to all of you, but I'll mention anyway, because there is this confusion of associating ontologies with things which are specified in OWL. From the same conceptual model, we can generate many different implementation, addressing different sets of non-functional requirements, different design concerns, right? So from this OntoUML conceptual model, we can generate a relational database, for example. And in fact, we have an approach for doing that. So normally when you go from an object-oriented model to a relational model, you have to make choices, right? What do you do with this taxonomy? So there is this approach of one table per class, one table per hierarchy, one table per leaf node, and so on. What we have here is what is called a one table per kind, which relies on that strategy of abstraction that we saw. And there are many advantages. We have a paper showing the advantages of this approach of one table per kind. And we also generate the OBDA mappings as well, as I mentioned before, automatically. We can generate code in many different languages, and we can generate models in OWL. So OWL, in our view, is basically an implementation language. It's a language, it's, you know, in the same way Prolog is an implementation declarative logical language, OWL is a declarative logical language. And it's useful for some applications to address some design problems, but you should never start building your domain models, your conceptual models in OWL, in the same way that you shouldn't do it using relational algebra or Java or anything else, right? And now, once you have your OntoUML model, again, we can generate code in OWL. There are many ways of doing this because you have a difference in expressivity of these two languages, right? So you have this problem of, you have all these dynamic notions. How do you map these dynamic notions to a language that doesn't have any notion of temporality? And also a language in which you cannot use the old AI tricks of time indexing all relations. So you cannot say John is married to Mary at time T1, but married to Clara at time T2, because the relations are all binary, right? So you cannot do that. So there are several different ways of circumventing that limitation, let's say, and this will generate different implementations. In order to assist this implementation, we have an OWL representation of the Unified Foundation Ontology, which is this ontology in the background of OntoUML. It's called GUFO. Luciana will get the joke, for example. GUFO stands for Gentle UFO, but it also means owl in Italian. And so it's an implementation of the Unified Foundation Ontology using OWL. And then you generate this code, for example, that is structured according to that ontology. So here we have a superstructure, which is the GUFO implementation of UFO. And here you have the domain classes, right? Person and donor and donee and transplants and so on. So we have this in the tool, so you can just go there, choose one of these possible transformations. So there are many transformations, one that takes objects to be temporal worms, another one that reify all aspects and temporalize these aspects. We can get into this discussion if you're interested. The important thing is you generate this OWL code automatically from the OntoUML tool, including some of these rules, right? So the domain constraints in OCL, we map to swirl rules, and then you can use it to reason in your OWL tools like Protege or OWL reasoners, right? So you can, because this is a logical language that supports automated reasoning, you can use to infer information from the information which is represented there. Another thing you can do is to deal with this problem of validation. So just to make this very explicit, verification, what we had before was verifications, checking consistency and satisfiability of the model, right? Verification is, did we build the model right? Validation is, did we build the right model? So is the model that we have the one we should have, the one that truthfully represents our conceptualization, our intended conceptualization of the domain? So verification is a problem that can be dealt with only by looking at syntax and formal semantics. Validation is a problem of real world semantics. Is the model that you have there the model that you should have, right? And it's much harder to automate, obviously, because you are comparing two sets, the set of possible interpretations of a model with the set of intended interpretations of a model. The problem is set B is in the mind of the modeler or the community of modelers. Set A can be automatically generated, right? So we thought that by automatically generating the set A, we could present to the modeler what that model is saying on their behalf, so that the modeler would detect cases in which these two sets are not the same, in which they deviate from each other, right? So ideally, they would be the same. I mean, the only possible interpretations of the model are the intended ones. However, very often there are missing constraints in the model, so the models are under constrained, and therefore there are possible interpretations which are not intended, like, for example, in which I'm my own ancestor, or and so on which people are living and deceased at the same time. And sometimes the model are over constrained, in which, for example, people would say that the only two possible genders are men and women, right? What do we want to do? The problem of domain modeling in that sense is finding out the exact set of constraints that would make these two sets match. This is fundamental for this problem of interoperability that we saw before, because if these models are too loose, for example, if they are too unconstrained, what can happen is that their possible interpretations might intersect without the intending interpretations intersecting, right? This is exactly what is called the false agreement, when we think we are talking about the same thing, when we falsely believe we agree. So this is another takeaway message, that if we are going to use these domain models to build these systems, which are a result of the interoperation of pre-existing systems, these models have to function as contracts, as meaning contracts. They are not, doodling mechanisms. They are really contracts telling the world, what is my worldview? What is the worldview which is embedded in that system? So the approach we use to address this problem is this approach of simulation. So basically use an extension of a formal language called Alloy. So we basically built a kind of model semantics on top of Alloy. And then what we do is that we automatically generate the possible interpretations of a given model. So for example, for this model, oh, by the way, there are we are talking about the approximation of these two sets, right? Some of these constraints, they come for free for us. Why? Because these patterns that we have here are representations of this underlying micro-theories. So every time I use a pattern like that, I would include a micro-theory, a particular axiomatization, right? So you have here, because I use this pattern, I will instantiate this axiom saying that every supplier is an active organization, that every supplier can cease to be a supplier. In all possible situations, if something is a supplier, there is a customer in which with which they contract and so on. So part of the axiomatization come from the patterns of the language, from the semantics of the language. However, this is not enough, right? Because the language, being a domain-independent system, cannot know about domain-specific constraints. I mean, no domain-independent system would know about the fact that you cannot come back from the dead, or that you cannot jump from being a child to an adult, or that you cannot marry yourself, or you cannot marry dead people, and so on, right? So the problem is actually finding out about this domain-specific constraints. So again, what we do is, because the set B is in the mind of the modeler, what we do is to automatically generate visual representations of the members of set A, of the possible interpretations of the model, such that the user is contrasted with what the model is saying on their behalf, right? So from this model here, we will generate instances, like for example, and then we can see that, you know, the same organization can play the role of customer in one economic agreement, while playing the role of a supplier in another agreement. But as we iterate through the possible interpretations, this will pop up. So this is an economic agreement in which the organization buys from more than one supplier, including itself. So it sells to itself, right? So it plays both the role of customer, of corporate customer, and supplier in the same economic agreement, which might not be desirable. Here's another example. Oh, by the way, this is caused by this portion of the model, right? It is exactly because here, both roles, quote unquote, in the scope of this relation, because one is not a role, is a role mixing, both roles in the scope of this relation can take their identity from the same kind. So if you have an economic agreement between a corporate customer and a supplier, both corporate customer and supplier are organizations. Of course, they can be the same organization. So in fact, this is a fragment that when present in a model can cause the dissociation between these two sets. So a pattern that captures a kind of error-prone configuration, an anti-pattern. So every time you have in the scope of a relator multiple roles that take their identity from the same kind, of course you can have at the instance level the same individual playing more than one role. Here's another example with the transplant that we saw before. So if I run a simulation of this model, this will pop up, which is good. So I can realize that given a transplant, I could have one donor, one donee, and several surgeons in the same transplant, but this will pop up. So it's me donating an organ to myself and performing the transplant, right? Or me donating an organ to someone else and performing the transplant, or me donating an organ to myself and someone else performing the transplant. These are all possible interpretations of that model, which we won't realize that these are possibilities there, right? And this is actually quite interesting as a, oh, by the way, when people look at this, and the first attempt to solve this problem is to declare these three roles as mutually disjoint. However, if you do that and you simulate this again, you're going to realize, and the tool will show you, that you have, that you then over-constrain the model, because now someone who donated an organ can never receive an organ as a donee. And a surgeon can never donate or receive an organ, right? So you're over-constraining the model. You're saying it's too strong to say that these three roles are disjoint. What you want to say is that they should be disjoint in the scope of the same transplant. So by playing the simulation game, you realize which are the constraints that should be included and excluded such that these two sets meet in the end. Here's, as I said, these are examples of this anti-pattern. Here's another anti-pattern, right? Because now what we did was, we ran simulations over many, many models in many different domains until we could find out these structures, these anti-patterns. So what we can do now with the tool is that the tool can proactively detect these anti-patterns in the model, show you why this might be a problem, right? These are error prone. These are kind of model smells. If we knew this would be a mistake, again, we could put an axiomatization that would exclude the situation in the grammar of the language, right? But these are sometimes a mistake. Maybe it is possible for people to donate organs to themselves and perform the transplant. And here is an important bit from the point of view of requirements engineering. This becomes an interesting technique for requirements elicitation, because now I simulate this, and these things will show up in the simulation, and then I come to the domain expert, and then I ask this question: is it possible for someone to donate an organ to themselves? And they'll say yes. I mean, skin is a type of organ. This is called, for example, auto transplant. I'm making things up. And then you find out that that's not only possible, but there is a hidden specialization of this notion of transplant, which would otherwise have remained tacit in the mind of the domain expert. So by playing the simulation game and interacting with the domain expert, this can play a role in the elicitation of tacit domain rules and tacit domain concepts. Again, once we have this catalog of patterns, we can put in the tool a mechanism to detect these patterns automatically. So here's another pattern, right? I have two types and a relation between these types, and then I have specializations of these types. Direct or indirect specializations, but I have another relation between the specialization of these types. What we found out is that typically there is a constraint between these relations, which people often omit. For example, my heart is composed of a ventricle, but in order for my heart to play the role of a blood pump, the ventricle has to play the role of a pump, right? So this is a model that looks sensible, but as I simulate this, I'll get this, that, for example, my heart is composed of a ventricle, Renata's heart is composed of a ventricle, but when my heart pumps blood, it pumps blood with her ventricle and vice versa. So this is a possible instance of that model. So what we did was to build this catalog of anti-pattern, and we implemented this in the tool. So the tool will detect these things, will show you why this is a problem, and will give you options on how to rectify the model, how to include constraints that would exclude this undesirable situation. So this is here is an example. The tool, okay, so this is, there is a model missing. Yeah, problem with the slides. The tool will show you all the anti-patterns that it has detected. We'll show you some constraints that it could include to exclude this model, and so on. Here is just one empirical work that we did in a repository of OntoUML models in many different domains, in many different sizes, and so on, just to give you an idea of how often these anti-patterns appear in these models. So, for example, here we have this relation specialization is the one that we saw with the heart example. It appeared 817 times in this repository. The association cycle appeared 1,800 times. So this is an example. So this is, for example, a detective that conducts an interrogation in a criminal investigation of which he's not part, right? So he's part of a criminal investigation, and he conducts an interrogation in another criminal investigation of which he's not a participant. So every time you have these cycles, you have potentially this problem. This is the one of the transplant, for example. It appeared in 25% of the models. Now we took the biggest model we had in the repository. We had nearly 4,000 classes, and it was built by a team of domain experts in a governmental application across 2 years. And we gave them the tool so that we could detect how often these patterns would really introduce an error, how often they would really open up the model to unintended interpretations, and how good were our refactoring, rectification options. So how often they would say, yes, I want to eliminate this, and how often they would accept our suggestions. And for many of these anti-patterns, this was actually quite positive. So for example, for relation specializations, in almost 90% of the occurrences, this was really a problem, and we could solve it automatically in 90% of the cases. In the case of the transplant, in 56% of the cases, it was a problem, and we could fix in 77% of the cases, and so on. So I'll just go through two very quick things. One is that then we tried something very daring. We thought about looking at anti-patterns in really, really, really big models. And we started looking for anti-patterns on Wikipedia, right? So this is an example that we had of what is called, we saw this before, a type whose instances are types, right? So here we have people and the three phases of people. And we want to say that these phases are instances of a second order type. So I'm an instance of adult person, but adult person, the type is an instance of a person developmental phase, right? Now, this is very common on Wikipedia. And what happens there very often is that people mix up the two things. They mix up the specialization with the instantiation. So they, for example, here you have the class Z on the left, which is a specialization of class A, but at a certain point, someone also declares that Z is an instance of A, mixing up these two notions, right? So people say that, you know, scientist is a specialization of profession, that a computer science is a scientist and is a profession, but they also declare that scientist is an instance of profession, right? And then you get this strange inference that Tim Berners-Lee becomes a profession, for example. So what we did was to detect these anti-patterns on weak data, and weak data is what people believe is the consistent, well done part of Wikipedia, right? It's the data structure behind Wikipedia. Now, the number of classes in taxonomic hierarchies in weak data when we published this paper were 337,000 classes. The number of classes that span more than one of these levels, that you have this multi-level thing, it was 70,000 classes. And only that first pattern appeared in 15,000 of these hierarchies. So 85% of these hierarchies were just logically inconsistent. Now, this is the very last thing. We wanted to do the following. Once we have the simulations, right? So what the tool does is the tool will present all these possible interpretations of the model, and the user will look at each of these instances and say, yes, I want this, I don't want that. After a while, we realized that this was very important information, that the user, as the user would go through the set of possible interpretations, telling which ones were intended or non-intended, the user was actually curating a database of examples and counterexamples of the model, right? Then we thought, like, you know, if we have, because all anti-patterns we have so far, they were manually discovered. So we basically simulated many models in many different domains, and then we start looking, these things started to emerge, these structures, right? But we thought, can we, I mean, I'm sure there are many anti-patterns we are not aware of. Can we learn these anti-patterns automatically from a curated database of intended and unintended models, given a particular domain model? Intended and unintended interpretation given a particular domain model. Then we thought this would be the perfect scenario for a particular machine learning approach. which is inductive logic programming. So in the inductive logic programming, if we have a background theory and a database of examples and counterexamples, in theory, we could learn what are the constraints that should be included in the background theory, such that all intended examples, all examples become valid interpretations of the background theory, and no non-intended, unintended counterexamples will be excluded, would not be valid interpretations of the theory. Then we thought, our domain model is the background theory, and as the user simulates this thing, the user is giving us information, important information of examples and counterexamples. So just to give you an idea of a very, very simple model, suppose I have this person, man and woman, and this is the logical rendering of this thing, right? Saying every woman is a person, every man is a person. Suppose I simulate this, and these are the possible instances that the tool will show you, right? And then you have all these cases, like, that here there is an instance of someone who's a man, someone who's a man and woman at the same time, someone who's a person, but neither a man nor a woman, and so on. And imagine the user can now mark this, that which of these are intended and which are not intended. So this approach would allow you to learn certain patterns here, that there shouldn't be a person who's neither a man or a woman, and that according to this particular set of choices, there shouldn't be someone who's a man and woman at the same time. Now, we can learn these constraints and then include automatically these constraints in the model. So we are doing this so we can learn all the anti-patterns, that we can learn the equivalent of axiomatization for all the anti-patterns we knew about. We are not yet able to learn new anti-patterns because we have to learn constraints and find out, generalize these constraints across different models and different domains. But that's exactly what we're working on right now. And we have a first paper on this. If people are interested, I'll be happy to share. So this is the slide that is in the wrong position. A very simple model. In this simple model, we have 13 anti-patterns, right? Maybe you can already identify this. Here we can have, people being both a parent and a child in the scope of a relationship. We have a detective conducting an investigation an interrogation and a criminal investigation of which he's not part. We can have in the scope of a criminal investigation the same person being the detective, the suspect, and the witness, or two of these pairwise, and so on. So the tool will detect all these cases and show you these rectification options. And by checking boxes and so on, it will generate automatically some constraints to be included in the model such that these anti-patterns, if really errors, they should be excluded. So here are my takeaway messages from the first part. Domain appropriateness is a fundamental quality for software systems, because software systems are representations of reality, and modern software systems are representations of reality which are collectively collectively constructed in a distributed way, right? By assembling worldviews which were developed in a kind of autonomous and concurrent way. So domain appropriateness requires appropriate domain models or domain ontologies in the sense that I discussed in the beginning of the talk. Ontology building is a very complex, it's a vastly complex activity. So there is a mistake here, especially in critical domains, right? So if we're doing, pizza ontology, that's fine. I mean, we can use any type of language or tool, but if we are building ontologies in critical domains, in finance, in healthcare, in security, and so on, it's very easy to make mistakes, right? In fact, it's funny that when we started using this validation tool, we realized that it's basically impossible to build a model that wouldn't contain a validation mistake. It's impossible for us to calculate all possible interpretations of the model, especially because of this model semantics, because things change in time, right? Verification is a different game. I mean, after you know enough logics and you've been doing this for a while, you don't make verification mistakes, but avoid validation mistakes is very hard, and especially hard when the domains are complex and the models grow big. So we need the correct tools. We need a kind of humble approach and realize that this is complex and we should have the, get hold of all possible engineering tools we can to assist us in this activity. And finally, this is the main takeaway message, is this one: no ontology without ontology. So we shouldn't build these domain models, this ontology embedded in software systems without this support of ontological analysis and the ontological toolbox I've been talking about, right? We should rely and leverage on the accumulated knowledge of this area that exists for more than the 2 millennia, and that exists in ontology engineering, in formal ontology, in applied ontology, in philosophy for 30, 40 years, and avoid reinventing the wheel. Like, for example, I mentioned before that UML has this very poor theory of parthood in which you have aggregation and composition. Why, instead of building your own theory of parthood, the language doesn't look into this area of mereology that exists for 100 years, right? That has very well specified axiomatized theories of parthoods that we can reuse, right? We can reuse by embedding them in a language system and in a tool ecosystem. So no ontology without ontology.